Okay, and now is the time for the last presentation, which will be done by me again, right? And it's about the Tesla magnifying transmitter experiment we are doing here in Czech, right, in Prague. Very well, so good, so that's my first slide. I must say that these kind of experiments which we are doing now, and I will present them, are relatively new. So I believe that in a couple of weeks or so we will have more and more kind of results. The number of interesting results is growing. So if we can go to next slide, first of all I will present what is our inspiration. So I think the biggest inspiration, of course, is Nikola Tesla, who is a main kind of who triggered all this research. And I found a couple of people from a kind of recent time which are very, knowledgeable about what Tesla was doing. For example, Peter Lindemann books The Free Energy Secret of Cold Electricity. I really recommend this book. It's very nice and inspiring. Then Secret of Cold War Technology by Jerry Vasilatos is amazing book. Actually, I was so impressed by this book that I wanted to translate that into to Czech language. And what I found is something which is really characteristic for this Tesla research, because a lot of people are speaking about Tesla, right, these days, but not really everybody has proper knowledge, I would say, and understand what Tesla was doing. I myself also, I think that it's much more important kind of to look at Tesla papers and patents with right knowledge, such that you can really acknowledge what the Tesla research means, right? There was one sentence also, or one comment in the book, and he said, look at the mainstream media to see how they treat Nikola Tesla these days. And then I Google and ask, some paper or article about Nikola Tesla. You can also do it, and you will find really very funny kind of papers related to that Tesla, okay, he was kind of, right, he was brilliant scientist, but he really didn't discover many things, alternating current and so on. But, a very strange kind of statement about Tesla these days. But I think, to my opinion, Tesla was probably the most brilliant scientist all ages and so on. I really have a hard time to understand everything what he has done, and to my opinion, we are now at the very beginning, and we are kind of scratching the tip of the iceberg with those experiments we are doing now. So there is much more yet to be discovered, right? Then another inspirational guy is Eric Dollard. I read some of his books where he is kind of trying to explain which kind of mathematics Tesla was using for his kind of research in polyphase and so on. And to my opinion, it is very closely related to quaternion algebra, which has been discussed this morning. The hypercomplex numbers and so on. But right, so Eric Dollard is one of the kind of, some people consider him as a living Tesla these days. And many inspirations I found also in videos of Adrien Marsh, and he has the link to his web page where he is presenting a lot of discoveries and interesting things. I even didn't have the time to went through all of this. There's really a lot of material, very interesting material about that. So majority of what we are doing was inspired by Adrian Marsh, right? Very good. So we can go to next slide. So what I'm going to present now, it's, I think it's related also to motto we have in our laboratory, which says, say what you do and do what you say. I think I like this, and I don't want to spend too much time to explain, but I hope you also understand what I mean by that, right? So if we can go to next slide, right? We are speaking here about the electric power system in the 21st century, right? And I like actually the quotation of Albert Einstein, who say, no problem can be solved from the same level of consciousness that created it, right? I think that's very deep idea, that if you want to solve a problem, you really have to step up from the level of the consciousness where the problem arose, right? So, to my opinion, majority of known kind of, I put in the quotation mark, free energy technologies reflect principles discovered already by Nikola Tesla. Why I put the free energy device in quotation mark is because there is a lot of confusion, to my opinion, ongoing confusion related to what the free energy is. As we said in my previous presentation, that the solar panels are also the free energy devices in a way that the COP, they are over unity devices and so on. So I believe that there is a possibility, or there are many possibilities to explore also different mechanisms than the solar energy or wind energy and so on, where we can kind of explore also the principle of quantum mechanics, zero-point energy, and so on. In order to make a progress in the electric power system towards the kind of future, I believe we need to re-examine concept of space-time continuum. I already discussed that. Gauge freedom, to my opinion, very important kind of misleading situation in concurrent understanding of the QED and the classical electromagnetism that we have, we are using the, so to speak, free gauging of the vector and scalar potential in a way that we believe that these potentials are pure mathematical construction. However, the quantum mechanics, Ahamorov-Bohm effect, and so on show us that this potential might be as real as the electric and magnetic fields. And to my opinion, we have also to re-examine the concept of ether, right? We also discussed the Michelson-Morley null experiment, but it doesn't really necessarily mean that the concept of ether should be rejected forever. As already mentioned, that also Einstein admitted this idea. So can we go to next slide? Few bold statements, right? Electromagnetic phenomena in the field of high voltage and high frequencies are key to understanding this new physics. I think in the region of high voltage and high frequency, there are really many of the new phenomena which is difficult, or to my opinion impossible, to accommodate into the concurrent classical electromagnetic theory. So there are yet unrecognized physical field, which Tesla called radiant, or nowadays we call it scalar, etc. Then there is also a phenomenon related to, if you measure the VI characteristic in high voltage discharges, then you see that the VI characteristic shows something what we call the negative resistor. There is a lot of ideas going in towards the, as discussed already, the power transmission, Zenek waves, and so on, single wire electric power transmission. Then we have discussed a lot of today about this observation of superluminous phenomena, Coulomb wave, etc. Then, as we learn from Professor Assis, the Weber electrodynamics maybe also allows us at some point to understand the universe is actually electric, right? So that's the notion. I think there exists a huge community of people who are really working on the electric universe theory, right? It will allow us, to my opinion, also to understand more clearly what gravity is. And we also see in this region a new type of phenomena like cold electricity, etc. You know, I will show you later, you know, these effects are, I think there are so many strange effects which we have no clue yet what it really means. So if we go to next slide, Kuhn van Vlaanderen already mentioned here this example of the Russian group, Russian team, Strebkov, who they have published, or somehow you can find the paper with the title of Single Wire Electric Power System for Renewable-Based Electric Grid, right? So the paper is from 2000. I think there are also some newer version. The idea is here that you use something like a Tesla transmitter to generate very high tension and high frequency field, and this kind of electricity can be transported over the thin wire to the receiver, where in the receiver stage could be either some some system like a Gratz bridge, or you can use a step down Tesla transformer again. And the resonance mode of oscillation with frequency about 30 kilohertz was used to provide the most efficient power transmission. It was experimentally proven that this SWEPS has quasi-superconductivity properties. I just pick up a couple of sentences from this paper because I think it's really opening a very interesting new era for the research, right? So the next slide. Yeah, I'm speaking about this Tesla magnifying transmitter. So I put some, complicated, for simple words for layman. What the Tesla actually, what the transmitter, what it does, right? So Tesla use an inter-resonant interaction between two resonance circuits. I call it sometimes also meta-resonance interaction. The resonance, I think everybody knows that if you have a pendulum, right? So in order to keep the pendulum running, you have to push it in the resonance way, right? So you cannot push it arbitrarily, so that's the meaning of resonance, right? But if you, maybe not so well known is that if you have two pendula, kind of, coupled pendula, then if they are in the resonant mode, it means that they have the same properties, right? Then, and you let one swing, for example, the red one, then you will realize that after a while, the energy from the red pendulum is transferred fully to the blue pendulum, so the oscillation in the red pendulum will almost cease, and you see the maximum on the blue pendulum, and then the energy is returning back to the red, and so on and so forth. So that's also the basic idea between the Tesla magnifying transmitter, that you have two electrical pendula, let's say two electrical resonance circuits, LC, L1C1 and L2C2. And if you bring the one resonance circuit into an action, so it starts to resonate and it transfers the full energy into the other resonance circuit and back and forth. This process is time to time also called a beating, right? If we go to the next slide, please. Right, so that's kind of very schematically the full kind of design of the Tesla magnifying transmitter. So you usually have a transformer, the high voltage transformer, 10 to 50 kilovolts, for example. And then here you have a primary circuit which is closed by so-called sparking gap. The idea is that whenever the transformer will start to charge the capacitor here, that at the moment the capacitor reach the high voltage, right, then the sparking gaps get shorted, and there will it will form the separated kind of primary LC resonating circuit. There is also the secondary coil, which has many more turns and higher high L, the higher inductivity. Coil has inductance, right? The high inductance, and but there is no C, and there is no capacitor, but the capacitor is kind of parasitic in this case, right? Because there is interwinding capacity and so on. So if we go to next slide, please, then at the moment the sparking gaps kind of get shortened, then you have isolated LC circuit, we call this primary LC resonance circuit, with the primary resonant frequency, right? So this is typically tuned by the value of the capacitor and the coil. And if the secondary coil is tuned to the same frequency or similar frequency, then the energy stored in this system, which is typically a couple of even joules, is transferred to the secondary circuit and back and forth, right? And but if usually if the energy is transferred to the secondary circuit, then there is a kind of electrode high voltage end of the Tesla transformer, and usually what happens is that the high voltage, the huge tension on the hot end of the Tesla transformer will break through the air, and you will observe the discharge, and the energy is kind of wasted in the discharge. But if not, then you usually see this kind of beating between the primary and secondary circuits. Very good. So we can go to next slide, I believe. Right. So this is a picture of one our, that's version number 16 or so, Tesla transformer we built in our laboratory. So here you see a kind of this high voltage transformer, which is made of three these are microwave oven transformers. Each, I believe, provide up to 15 kilovolts with the Villard doubler. So at the end we have something like 30 or 40 kilovolts, right? Then there is a spark gap here. This is our special design. And this is kind of 9 stages spark gap, which is very suitable to provide very sharp, high frequency switch, right? Then we have forgotten tool here, and the primary capacitors are here, and this one, that's the secondary coil. In this case, we have used something with 200 turns, and the primary coils are on that part. It's not so nicely visible, right? So if we go to next slide, just for people who would like, for example, to replicate this experiment, I will give more details about this secondary coil. Sorry for that. So we kind of use the formula for the inductance calculation. This is very simple calculation for the solenoid coil, and here you have this in this table are summarized the main kind of properties of that coil. We have 200 coils, the wire diameter 1.7 millimeter, then calculated inductance 570 microhenry. What we measure with the LRC bridge is 609, so very close, very nice. Then the important thing is that the coil should have an aspect ratio. It means the diameter and the length should be of, close to 5. So in this case we have 4.3, that's fine. The wire length is 50 meter. It means that the lambda 4, so in order to have the maximum voltage at the hot end, you have to set it up such that it generates kind of the lambda 4 antenna. And in this lambda 4 frequency, in this case, is 1.5 megahertz, right? So we can go to next slide, please. in order to tune, kind of to understand the frequency matching, I was also inspired by Adrian Marsh, and we used the vector network analyzer, this DG8SAQ. That's the low-cost 1.3 gigahertz vector analyzer, which you can order from internet. I will recommend everybody who wants to do something with the Tesla transform. That's very important device. Right. So if we go to next slide. That's the example of what Adrian called the series FET, right? So we take the secondary coil as, isolated from the rest of the system, and we hook it up to this VNA, this vector network analyzer, and we use this TX output, right? And, the one leg of the output goes to the coil, and the second one is grounded. And this is what you typically see. Right, so what is plotted here is the graph. One of the x-axis is the frequency in megahertz, and on the y-axis it's either in blue is the impedance, the absolute value of the impedance of that coil, and in red is a phase difference between the voltage and current. So if you are in the resonant mode, then this phase shift, kind of what happened is the phase transition, the full swing between plus or minus 90 degree, right? So, and also there are two modes of the two resonant mode. One is a serial mode. It means that you have your LC, your coil and the capacitors are in series. And if they are in the resonance state, then the impedance of such a circuit goes to 0. Or you can have a parallel mode, right, when the LC are in parallel, and then the impedance in the parallel mode goes to high value, kind of infinity. And that's exactly what we see here. In this place, which is 2.13 megahertz, we see the minimum impedance and the full phase swing, right, which is the characteristic of the serial resonance mode. And next to it is the parallel mode with very high impedance. The impedance is jumped from 290 ohm to 121 kilo ohm, right? So the very high impedance and the frequency of this first parallel mode is 2.6 megahertz. And then you see the kind of replication, and these are higher harmonics, right? So this is very kind of interesting plot which you can do with this VNA, which allows you to characterize every kind of single coil before you use it for any measurements and so on. So the idea is, what we are learning as we speak is to, if you are designing the secondary coil, you have to take into account the lambda 4 effect. So you have to choose the right wire diameter. You have to choose the right area kind of diameter in order to get the aspect ratio close to the 5, and many other things like that. So, and then you measure without any discharges, just in the, without high voltage, you can kind of see the spectrum and then to decide whether it's good or not. So, next slide. Then the other kind of tuning is already involved the complete Tesla magnifying transmitter system, where you put the secondary coil inside the primary circuit, and you measure the LC primary in the parallel mode, right? So that's kind of what Adrian Marsh called the primary FET. So if we go to next slide, and this is kind of the results you like to see, right? So in blue, again, it's the absolute value of the impedance, and in red is the phase shift between the voltage and current. And what you see here is this serial resonance of the whole system, which in this case is 1.9 megahertz, right? And then you see on the left and right side of this resonant mode, you see two parallel modes, primary parallel mode and the secondary parallel mode. And they are kind of shifted by half of the megahertz or so. And the tuning now, if in this situation, is that you have to either tune a little bit the primary inductance, or if you have a variable capacitor, so you vary the primary capacitor, and you have to do it in a way such that the impedances will be of the same order. And you'll see that it's not what we have at the moment, because we kind of lost one of the variable capacitor, but right, so that's just interesting. So this is, you know, the working mode of the Tesla transformer. You see the resonant frequency, which is a serial, and then two kind of side peaks characterizing the parallel modes, right? So if we go to next slide, please. This is the snapshot from the real measurement, which we have done with our oscilloscope, where we can do the Fourier transform. And we clearly see here the peak is not very nice kind of in this. We have also some other tools to measure the Fourier spectrum. But the nice thing is that, you know, the Fourier transform shows a clear peak at 1.83 megahertz. And VNA, you know, without the high voltage analysis, shows us 1.89 megahertz. So these two frequencies are very close to each other. So I believe that this kind of shows that we understand how to tune this Tesla magnifying transmitter. Good agreement, right? If we go to next slide, and now, so what we can do with the Tesla transformer. So this picture I call what does a layman sees, right? So that's why I also, for many years, I was not really enthusiastic about doing the research with Tesla transformer, because I saw a lot of YouTube video with this kind of show in the discotheque, and people are dancing with music and with this discharges kind of, you know, so I said that's not really what I want to do in my lab, right? So if we go to next slide, but then I realized that there is actually a lot of things of what you can see. So what do I see is a new type of electromagnetic phenomena. That's the kind of snapshot from one of the experiments. You see my colleagues, Jakub Malina, that's me, and so on. When we kind of took a picture of the magnifying transformer, when it's tuned to roughly 1.9 megahertz, the voltage at the end, roughly, we don't know exactly, but it's about 100,000 volts, right? And we see a lot of interesting phenomena. First, this violet, so to speak, glowing around is very beautiful. It's amazing, right? But it has much deeper meaning than what I can tell you now, right? If we can go to next slide, I didn't have too many details about that, but if you look closely how the discharges looks like, you will find that these discharges kind of are very dependent what frequency your device is tuned to, right? If you are at low frequency, usually the discharges are very abrupt, you know, unpleasant, and so on. At higher frequency, the forming of the discharges starts to be very interesting. And I'm now maybe, I regret that I didn't include these slides, but you can also demonstrate that at some frequency, what you are observing is so-called golden dragon discharges, which are reflecting the Fibonacci numbers or golden ratio fractals, right? So, to my opinion, it's very fascinating. I don't have slides to support this statement, but you can find a lot of material in Adrian Marsh slides related to golden dragon discharge formation, right? So we do it as well, but this is not probably yet not the time to show it here. So at some frequency, the discharges are reflecting a new, very interesting kind of physics, which is related to some fundamental properties of the space-time in the region of high tension and high frequency, right? This is for another, maybe another presentation next time. So if we go to next slide, I will show you now the video from the laboratory just for fun. which we have recorded a couple of days ago. Right. So what do you see? The discharge from the hot end, right, which is not yet this fractal structure, but that's it. I think we have a longer. That's it. I think we had a longer video. Ah, sorry, thank you. You see this very nice, interesting structure and discharges over the whole, kind of the whole wire length up to the hot end, right? You know, it looks like it's not so important for free energy or whatever, but I do believe I see a new phenomena here, which are not recognized by the concurrent, let's say, electromagnetic theory. I can tell you also that we see a lot of very strange effects. For example, this is an infrared camera, and we are measuring kind of the temperature of the surrounding materials, the wire itself, and so on. And we realize that if there is a metallic object close to to this transformer, then although it's completely cold, but if you touch it by hand, you will get burned. Right? Things like that, right? Very nice. So I think we can move on, if you allow me. Right. The last part of my talk I want to spend on the, to my opinion, very anomalous observation, and that research goes back to 1975. I found somewhere the references to the Kurchatov Institute paper, where people like Avramenko, Grachev, and Nikolaeva wrote a paper, Symmetry Violation of the Law of Electromagnetic Induction relative to the direction of the magnetic vector potential of the electromagnetic field. I will not go into the detail of that paper. It's very fascinating that already in 1975, you know, this is, sure, you know, all this knowledge came from Tesla, right? So it's more than 100 years old, but they were even kind of the scientific papers on this. Avramenko noticed that there is an anomalous DC potential which is created in the vicinity of Tesla transformer, and there is also the anomalous symmetry violation with respect of the direction of the magnetic vector. So I will not demonstrate here all this. So we are in the course of replicating this experiment. If you go to next slide, what we have realized that if you have a standard LC resonance kind of vibration, so it's always this oscillation goes around the zero, right? You have positive maximum, then zero, negative maximum, and so on. But what we have realized that in some circumstances, one can tune the Tesla magnifier such that you have the zero here and there is a pedestal, so to speak. So you see a pedestal, some kind of DC voltage, which shifts the oscillation towards some value, right? So it's kind of peculiar. There is a strong anomalous static potential which is felt everywhere around, you know, in the laboratory. We, for example, if we switch off the transformer, so after half an hour you enter back the laboratory and you get kind of spike of the discharges from the metallic object, half an hour after the experiment, right? And and so we see this, even if the secondary coil is grounded, so the origin of this DC potential, to my opinion, is not known, right? It generates very peculiar effects, and we can kind of measure this DC potential by the capacitive divider, right? So this I will show in the next slide. Right, so there is something anomalous that if you have, you know, right tuning in between the primary and secondary, then there is kind of the extra kind of DC current which is circulating around this kind of system, and where is the DC current is coming from I don't know yet, but this is kind of our what we are now studying, right? If you go to next slide, we can measure, and that's to my opinion extremely interesting. We can measure this DC current by this capacitive divider, right? So we have a capacitor, high voltage capacitor, and we measure the DC voltage which is generated on that capacitor. If the electromagnetic waves coming through the capacitor is the standard wave, right? So it's oscillating around the zero, then it cannot charge the capacitors to the DC potential, right? But it does. And what we can also do, that we can change the distance between the capacitive probe from the hot end of the transformer, and then in this way we can measure the value of that potential as a function of the distance. So we measure the spatial distribution of that potential, right? So if you go to next slide, I will show you one of the video what is happening. Actually, if you place this capacitor close to the transformer, then it can get charged to arbitrary value, right? So what you see here is the voltage differential probe measured on that capacitor, and this is that one you see, and we have a discharge here, because if the capacitor goes over the voltage, it will break the oscilloscope, right? And what you see here is the voltage which is increased, and then the discharge will discharge the capacitor, right? So, and that's you see as a flash here, right? So that's very kind of standard way how the capacitor is charging, right? I believe that it's understandable. We have realized that sometimes the flashes are so fast that we cannot catch them on camera, but right, and we also measure this DC potential, as I mentioned before, as a function of the distance from the hot end. And for example, here is one measurement. We see the average DC voltage on that capacitor was of order of 3 volts, and then it grows up to 13 volts, and it drops again. And that's very first measurement, but to my opinion very intriguing, because you see there is a kind of standing waves created in the free space, which is, I think nobody has ever seen that, to my opinion. And the characteristic width of that spatial distribution is very preliminary, but so I didn't put any errors and so on, but the characteristic width is 28 millimeters, right? And if you then recalculate by use of speed of light in vacuum, what that would be the frequency, you will get that the characteristic frequency for that scale would be 10.7 gigahertz, right? So to my opinion, very interesting observation. So first of all, there is a standing wave formation, right? And these standing waves are made up from the static DC potential, right? And the characteristic frequency is 10 gigahertz, right? To my opinion, very interesting. So if we go to the last slide, I believe, so we are observing already now anomalies, DC current in totally symmetric circuit. There are no diodes or no rectifier, and still you have a DC component, right? It charges capacitor to infinitely high voltage. If we don't have this spark gap, then probably the capacitor will blow up, right? The DC current forms standing waves, right, which I have no clue how come that in the free open space you have a standing wave, kind of where the maxima and minima are kind of fixed within the distance from the hot end. And the characteristic length give you a 10 gigahertz frequency, which is, to my opinion, very interesting observation. I am not making any further conclusion besides that it's not even the beginning, maybe just the beginning. So thank you for your attention. And I think